In mathematics, homogeneous coordinates or projective coordinates, introduced by August Ferdinand Möbius in his 1827 work Der barycentrische Calcül 1/4L, are a system of coordinates used in projective geometry, as Cartesian coordinates are used in Euclidean geometry. They have the advantage that the coordinates of points, including points at infinity, can be represented using finite coordinates. Formulas involving homogeneous coordinates are often simpler and more symmetric than their Cartesian counterparts. Homogeneous coordinates have a range of applications, including computer graphics and 3D computer vision, where they allow affine transformations and, in general, projective transformations to be easily represented by a matrix. If the homogeneous coordinates of a point are multiplied by a non-zero scalar, then the resulting coordinates represent the same point. Since homogeneous coordinates are also given to points at infinity, the number of coordinates required to allow this extension is one more than the dimension of the projective space being considered. For example, 2 homogeneous coordinates are required to specify a point on the projective line and 3 homogeneous coordinates are required to specify a point in the projective plane. Introduction: the real projective plane can be thought of as the Euclidean plane with additional points added, which are called points at infinity, and are considered to lie on a new line, the line at infinity. There is a point at infinity corresponding to each direction, informally defined as the limit of a point that moves in that direction away from the origin. Parallel lines in the Euclidean plane are said to intersect at a point at infinity corresponding to their common direction. Given a point on the Euclidean plane, for any non-zero real number z, the triple is called a set of homogeneous coordinates for the point. By this definition, multiplying the 3 homogeneous coordinates by a common, non-zero factor gives a new set of homogeneous coordinates for the same point. In particular, is such a system of homogeneous coordinates for the point. For example, the Cartesian point can be represented in homogeneous coordinates as or. The original Cartesian coordinates are recovered by dividing the first 2 positions by the third. Thus, unlike Cartesian coordinates, a single point can be represented by infinitely many homogeneous coordinates. The equation of a line through the origin may be written nx plus my equals 0 where n and m are not both 0. In parametric form this can be written x equals mt, y equals nt. Let z equals 1 per ton, so the coordinates of a point on the line may be written. In homogeneous coordinates this becomes in the limit, as t approaches infinity, in other words, as the point moves away from the origin, z approaches 0 and the homogeneous coordinates of the point become. Thus we define as the homogeneous coordinates of the point at infinity corresponding to the direction of the line nx plus my equals 0. As any line of the Euclidean plane is parallel to a line passing through the origin, and since parallel lines have the same point at infinity, the infinite point on every line of the Euclidean plane has been given homogeneous coordinates. To summarize, any point in the projective plane is represented by a triple, called the homogeneous coordinates or projective coordinates of the point, where x, y and z are not all 0. The point represented by a given set of homogeneous coordinates is unchanged if the coordinates are multiplied by a common factor. Conversely, 2 sets of homogeneous coordinates represent the same point if and only if one is obtained from the other by multiplying all the coordinates by the same non-zero constant. When z is not 0, the point represented is the point in the Euclidean plane. When z is 0, the point represented is a point at infinity. Note that the triple is omitted and does not represent any point. The origin is represented by equals notation equals. Some authors use different notations for homogeneous coordinates which help distinguish them from Cartesian coordinates. The use of colons instead of commas, for example instead of, emphasizes that the coordinates are to be considered ratios. Square brackets, as in, x, y, z, emphasize that multiple sets of coordinates are associated with a single point. Some authors use a combination of colons and square brackets, as in, x, y, z. Other dimensions. The discussion in the preceding section applies analogously to projective spaces other than the plane. So the points on the projective line may be represented by pairs of coordinates, not both 0. In this case, the point at infinity is. Similarly, the points in projective n-space are represented by tuples. Other projective spaces, the use of real numbers gives the homogeneous coordinates of points in the classical case of the real projective spaces. However, any field may be used. In particular, the complex numbers may be used for complex projective space. For example, the complex projective line uses two homogeneous complex coordinates and is known as the Riemann sphere. Other fields, including finite fields, can be used. Homogeneous coordinates for projective spaces can also be created with elements from a division ring. However, in this case, care must be taken to account for the fact that multiplication may not be commutative. Alternative definition: another definition of the real projective plane can be given in terms of equivalence classes. For non-zero element of R3, defined to mean there is a non-zero iso that equals. Then is an equivalence relation, and the projective plane can be defined as the equivalence classes of R3 is 0. If is one of elements of the equivalence class P, then these are taken to be homogeneous coordinates of P. Lines in this space are defined to be sets of solutions of equations of the form x plus y plus cz equals 0 where not all of A, B and C are 0. The condition x plus y plus cz equals 0 depends only on the equivalence class of, so the equation defines a set of points in the projective plane. The mapping A defines an inclusion from the Euclidean plane to the projective plane, and the complement of the image is the set of points with z equals 0. This is the equation of a line according to the definition, and the complement is called the line at infinity. The equivalence classes, P, are the lines through the origin with the origin removed. The origin does not really play an essential part in the previous discussion, so it can be added back in without changing the properties of the projective plane. This produces a variation on the definition, namely the projective plane is defined as the set of lines in R3 that pass through the origin, and the coordinates of a non-zero element of a line are taken to be homogeneous coordinates of the line. These lines are now interpreted as points in the projective plane. Again, this discussion applies analogously to other dimensions. So the projective space of dimension n can be defined as the set of lines through the origin in Rn+1. Homogeneity: homogeneous coordinates are not uniquely determined by a point, so a function defined on the coordinates, say f, x, y, z, does not determine a function defined on points as with Cartesian coordinates. But a condition f, x, y, z, equals 0 defined on the coordinates, as might be used to describe a curve, determines a condition on points if the function is homogeneous. Specifically, suppose there is a case such that if a set of coordinates represent the same point as, then it can be written for some non-zero value of I. Then a polynomial g, x, y, of degree k can be turned into a homogeneous polynomial by replacing x with xz, y with yz and multiplying by zk, in other words by defining the resulting function f is a polynomial, so it makes sense to extend its domain to triples where z equals 0. The process can be reversed by setting z equals 1, or the equation f, x, y, z, equals 0 can then be thought of as the homogeneous form of g, x, y, equals 0, and it defines the same curve when restricted to the Euclidean plane. For example, the homogeneous form of the equation of the line x plus y plus c equals 0 is x plus y plus cz equals 0. Line coordinates and duality. The equation of a line in the projective plane may be given as sx plus ty plus rs equals 0 where s, t and u are constants. Each triple determines a line. The line determined is unchanged if it is multiplied by a non-zero scalar, and at least one of s, t and u must be non-zero. So the triple may be taken to be homogeneous coordinates of a line in the projective plane, that is line coordinates as opposed to point coordinates. If an sx plus ty plus rs equals 0, the letters s, t and u are taken as variables and x, y and z are taken as constants, then the equation becomes an equation of a set of lines in the space of all lines in the plane. Geometrically it represents the set of lines that pass through the point and may be interpreted as the equation of the point in line coordinates. In the same way, planes in 3 space may be given sets of 4 homogeneous coordinates, and so on for higher dimensions. The same relation, Sx plus Ty plus Rs equals 0, may be regarded as either the equation of a line or the equation of a point. In general, there is no difference either algebraically or logically between the homogeneous coordinates of points and lines. So plane geometry with points as the fundamental elements and plane geometry with lines as the fundamental elements are equivalent except for interpretation. This leads to the concept of duality in projective geometry, the principle that the roles of points and lines can be interchanged in a theorem in projective geometry, and the result will also be a theorem. Analogously, the theory of points in projective 3 space is dual to the theory of planes in projective 3 space, and so on for higher dimensions. Pla 1/4 scalar coordinates. Assigning coordinates to lines in projective 3 space is more complicated, since it would seem that a total of 8 coordinates, either the coordinates of 2 points which lie on the line or 2 planes whose intersection is the line. A useful method, due to Julius Pla 1/4 scalar, creates a set of 6 coordinates as the determinants xi ijxjyi1 a per mil currency I.